All right, recording 3 started. So what I wanted to do with this is, oh, whoops, sorry, that's wrong. So here's the start you guys started with. Is go over what would the ideal textbook solutions be to each of these 10 mini labs. So the first one was just very simply hang different lab masses, like lab weights from these spring scales, see what you get. You guys had a whole box of lab weights thrown on here. I'm going to make up some masses. Let's say you had 100 grams, 200 grams, 500 grams, and 1,000 grams. The largest lab weight has a mass of 1,000 grams, right? Which is also called what? 1 kilogram. Now, kilogram actually is the base SI unit for mass, and that's about to become really important. Like start today and go for it. But grams or kilograms, I might just use grams today because a little bit more practical for the setting. Right. Now, if you weighed each one of these, what do you guys get for let's say the 500 grams lab mass? What do you guys get for the weight? About how many newtons?
5.
There you go, 5. That's what I'm looking for. About 5 newtons. What about the 1 kilogram? How much does that weigh? 10 newtons. Right, good call. Right. If you want to be more precisely, it's actually how much gravity force, how much weight. 9.8 newtons. Right. Now, more often than not, I'll go ahead and round to 10 newtons. AP is okay with you doing that. And also these spring scales anyway. It's like, well, how much precision can you really get out of this? Right. So let's call this guy 2 newtons and 1 newton. Okay. So right now on this graph, what's the force in newtons? Now, you guys know force is a vector. Looks like it has a direction to it. Right? Gravity's pulling straight down. Right? Weight straight down. Versus the mass in, well, let's just go grams today, right? Right. Which is, you guys know mass is like the amount of inertia, like something to do with it. Resistance to change in state of motion like that. Right? So let's scale this 0, 2, 4, 6, 8, 10 newtons. 0, 2, 4, 6, 8, 10 newtons. Let's scale the mass 0. Let's go 200, 400, 600, 800, 1,000. 200 all the way to 1,000. Here, I'll go ahead and fill these in. 400, 600, 800. Because I did see a handful of students who would do something like do 0 here, and then 100, and then 200, and then right next to that was like 1,000. So, guys, you guys see how my axes are scaled, but like they're spaced linearly, like spaced evenly, right? You guys see that? Right. You always either want to do that, or like if we manipulate axes, like there's such a thing as like logarithmic scaling. We go like 1, 10, 100, 1,000, something like that. Right? But typically, you'll have it this way, the way to we're like evenly spaced. What you don't want is like random spacing, like, oh, okay, well, I did 100 first, and then I did 200, and then I did 1,000, and I'll just like space it, right? Okay, you want to be actually like, otherwise you get graphs that make no sense. Okay? All right, let's see what this graph looks like. So 100 grams was 1 newton of weight, bam, right there. 200 grams mass was like 2 newtons of weight, bam. Something to do with Earth's gravity field is the relationship between these two, right? 500 grams, 5 newtons, bam. 1,000 grams weighed 10 newtons of weight. Bam. Okay. You guys see how these all line up in a straight line? Zip, you guys see that right there? Okay. I might write an equation for this. I'm going to say weight equals mg. Now that's mass times gravity field. That's 2 variables multiplied. Mass is the independent variable sort of here. And the slope is like Earth's gravity field. That's what G stands for. Lowercase g stands for in that context. Stands for like gravity field, right? Where you might see that. You guys remember very first day of school? Gave you guys this table. Look right here. Bam. You guys see m times g? Right. There's 2 variables multiplied. Whenever I do that, I'm talking about weight. Now, if you guys are taking some kind of medication one day and you see on the bottle it says mg, that refers to a unit milligrams. But that's not the case. This is a variable. Actually, it's 2 variables multiplied together. M times g to be weight. Right. AP will accept that to represent weight, or if you do F sub g, like force due to gravity. Okay, but more often than not, I do M times g. Okay, all right, so there you go. All right, let's weight mg. All right, you guys got on that one? Next one. What if you take a single weight and you pull it from 2 different spring scales? This guy got his walked off, but okay. Right, and you can kind of shift around. So maybe one scale is responsible for supporting more of the weight than the other. So suppose this guy right here is like 1 kilogram. Right, I got 1 kilogram lab mass, which weighs how much? 10 newtons, right? 10 newtons downforce, right? Which is the vector quantity, right? Now, if they're split half and half, that'd be how many newtons on the left and how many newtons on the right? 5 newtons and 5 newtons. It could be a 5-5 split like that, couldn't it? So it totals to 10 newtons. Right? Or you could have shifted them around, kind of like if you balance on 2 legs, you can shift your leg more to the left foot or the right foot, kind of. Right? What if I put 7 newtons on one scale pulling up? What's the other scale going to read? Ooh, that's down to 3. So with that, they still total to 10 newtons. What if I put 9 newtons on one scale? What's the other guy read? Should be down to 1 newton, so that they total to 10. What if I put all 10 newtons on 1? What's the other scale reading? There you go. Nothing. Zippity doo. So let's call it. Right. So they always sum to 10 newtons, right? Let me pick that second row, the 7 versus 3, right, and draw a free body diagram for this. Free body diagrams we're going to really focus on tomorrow. You're just picking a point and labeling all the forces that are on it. So that might be like 7 newtons from the spring force there, maybe like 3 newtons from the spring force there. You guys see 10 down and then 7 and 3 up. Ah, okay. That's why they always had to sum to 10, because the total force then, that makes it sum to 0. You got a total of 10 newtons up, 10 newtons down, right? That puts it in static equilibrium. Here's the principle that's being followed. The sum of the forces in the y direction goes to 0 newtons for an equilibrium case. Right? There's no net force. What does this look like on this graph? The force on the left in newtons versus the force on the right, also in newtons. Scale this 0, 2, 4, 6, 8, 10. 0, 2, 4, 6, 8, 10 newtons. 0, 2, 4, 6, 8, 10 newtons. 2, 4, 6, 8, 10 newtons. So you could have 5 and 5. Bam. You could have, let's see, 7 versus 3. Bam. I have 9 versus 1. Bam. Might have 0 versus 10. Bam. But there was an inverse type relationship, and it's also a linear relationship. Right? So any coordinate, it always sums to like the 10 newtons up to balance the 10 newtons down. All right. Okay. If you got that, and that's exactly what that graph should have looked like. Right? You guys good so far? All right, you guys ready to take this to 2 dimensions? You guys ready for 2 dimensions? All right, now this one right here, pay real close attention, think really deeply on this. I did walk around yesterday, I did see a handful of students, including in this class, get this graph correct. So really awesome if you did, because yeah, not too many students get that before I show how this works. Right, so we're gonna start out with everything just vertical, right? Let's say I hang a 1 kilogram lab mass, which weighs 10 newtons, right? Hey, do you guys think as I spread this out to more and more of a Y shape and gets closer and closer to a T shape, do you guys think that bottom spring scale is going to read 10 newtons over and over and over? Yeah, that one doesn't change. So force from the bottom spring, I'll go 10 newtons, 10 newtons, 10 newtons, 10 newtons. I'm just making up something for mine. If you chose a different lab mass, that's okay. Say 1 kilogram, right? Weighs almost 10 newtons, right? Then we're going to spread this out like a Y shape. And notice the angle that I told you to measure with respect to. So when you guys pulled out your protractors, you found like some kind of central node where they could all come together, and you lined up this node on the protractor, and you zeroed out the vertical. You guys see that vertical dashed line? And you're just measuring this angle right here. You guys see that? Okay. So start off 0 degrees. It's just like right here, right? And then make it wider, wider, wider. It gets closer to a T. Now, if you did have a perfect T shape, what would that angle be approaching? What 90 degrees, right? So maybe that's like an upper boundary, like it can kind of go up to there. So here's the 3 angles I'm going to pick. Well, 0 is already given. I'm going to go 30, 60, and then 80. And you guys are going to see why I picked those after I work this out. Okay. What's the force on each top spring? Maybe that's not the most scientific way to say it, but if you held it like symmetrically in balance, right? Like if it splits half and half, or they're reading the same value, right? So you're not putting more force on one than the other, right? I'm thinking for the first case, guys, if it's 10 newtons down, this is reading what and what up? 5 and 5, right? Which we already kind of did with the previous one. So this is kind of a continuation from the previous one. That would just be 5 newtons straight up, right? Now, what about when you start to spread it out? What did you guys notice happen to the force in each top spring when you started to spread out to like a Y shape? Did it stay the same? Or what did it do? Right. New poster time. Bing. Oh, look at this guy. It's a new poster. Oh, yeah. Hey, that looks exactly like what you guys did. You know what this also looks like? Does this look like the donkey question, sort of? This also reminds me of the donkey question, right? And of course, what we're talking about right now, right? But here's the principle. If you have a static situation so that there's no net force, right, the forces all have to sum to 0. There might be a bunch of individual forces, but the sum of the forces has to be 0. And in fact, if you introduce some kind of Cartesian system, maybe use your imagination or like sketch it out on paper, maybe have a horizontal and vertical axis, along each axis, along the x-axis, along the y-axis, the forces also have to individually sum to 0. Right. Show of hands. How many guys are possibly considering doing something engineering related in the future? Engineering related. Ooh, that's a bunch of guys. All right. Now, if you're a civil engineer, you think you might have to design some static structures, maybe like a truss bridge. Ooh, right. And if you're doing something more mechanical that's on the move, then this is just a step up to something even more complicated where things are like in motion. Right. Oh, yeah, go ahead.
How can I input, I guess, is that sigma into here?
Oh yeah, okay, so the sum of forces. All that means is like you're adding up all the forces, right? Here's what this means, right? So I got a spring scale pulling up to the right, up to the left, and then the weight's pulling straight down, right?
Adding up.
Yeah, so the amount that this guy pulls to the right is this right here. The amount this guy pulls to the left is this right here. See how I split it into components, right? Up to the right, up to the left, right? So the right part and the left part have to balance out. That's why they're zeroing out. So if I add this to this, got a positive value and a negative value. That's why it sums to 0, right? And then what about the vertical components, right? So each of these spring scales is pulling partially up, not exactly up, right? But partially up. And these two upward components better balance with this downward force, right? You guys see that? That's what this condition means right here. The sum of the forces in the y direction zeroes out, right? You see it, right? Now for my engineering example, again, so suppose you put together like a truss bridge, right? It has like a bunch of joints all which way. Some of these joints might be in compression, some in tension. That's one of the things you have to figure out. This is a tension example, of course. Right? But the next step from an engineer's point of view is you want to say, well, I'm building this bridge out of materials. So once you've figured out what the forces are along each branch, right, maybe you're building it out of concrete, maybe you're building out of steel. Those materials have different tensile and compressive strengths. So you have to know like what should the diameter of each bit be, right? And if you want to make this economical, right, then you want to do like what's the minimum size? So everywhere it's valid equal, right? So I'm not like, right, okay, right. So mathematically, right? So this is really, really, really foundational to like pretty much all of engineering, right? You guys see this? Right. So do you guys see if I have 10 newtons straight down, that and this is all symmetrical in this case, just pretty straightforward, that these two upward components better be like 5 and 5 to balance with the 10 down. You guys see that? Right? This better be 5 newtons and 5 newtons. Right? In fact, if these spring scales were straight upwards, it would be exactly 5 and 5 on each spring scale, wouldn't it? Right? And if you pull them at some angle, what should the force ratings be? Well, you guys figured out what the force ratings were on the scales empirically. You just grab it straight off the scale. So, it says like 7 newtons, 8 newtons, something. Right? But what should it like ideally mathematically be if we're solving this on paper? Now, I had you guys measure this angle right here. The way you did that with the protractor, took this node right here, popped it right here where they all come together, right? Zeroed out the vertical, because it said measure with respect to some imaginary vertical type line. You sweep out an angle this way. This one looks about like 55 degrees or so, 55 degrees on just, okay? Is that something like that? Okay. Now, guys, what's the relationship between this known vertical quantity? Now, this individually better be 5 newtons, right? This scale is responsible for holding half the total weight vertically. This better be 5 newtons. That's a known quantity. Also, you can measure this angle with a protractor, 55 degrees, right? And you want to know, ideally, what should the spring scale rating be? Right? Does that look like a sine, cosine, or a tangent relationship? What do you guys say? Let me draw this. We've got a known quantity, which is this component upward. Right, we've got some amount it's pulling to the right. We got the total force, which is the spring scale force. Right? This is known to be 5 newtons. You know this angle because you can measure with the protractor. And I'd really like to know what should be showing up on the spring scale. Right? Is that a sine, cosine, or a tangent relationship? Cosine. Yeah, cosine. Right? Cosine relates the hypotenuse of a right triangle, and that is a right triangle, right, to a leg that's adjacent to the reference angle, right? Which is exactly what we have here. Right? You might start with this. Cosine of the angle is equal to 5 newtons divided by the spring force, right? Or maybe you did it the way I told you the shortcut for this class, how you usually see it. Spring force times cosine of the angle should result in 5 newtons, right? Which you see those are just an algebra step away from each other anyway, right? But if you're trying to solve for what should the spring force be, you guys see that's going to be that component divided by cosine of the angle. Okay, so now we're dividing by cosine, right? You guys see that? Right. That's what I want to do for this table is take that right there and go right down this table and say, ideally, what should the spring force have been? Right, so let's check this out. Actually, let's look at the first one. So I'm going to take my 5 Newton component, again, each spring scale vertically holding 5, right? And divide by cosine of, now if I start at 0 degrees, I'm just referring to this picture right here, the 0 degrees from the vertical. Right? Because what is cosine of 0? 1, right? 5 divided by 1. Hey, it is 5 newtons, which got that already, right? You guys said this was going to be. Okay, I was just confirming that was going to be true, right? Sometimes it's good to confirm things you already know, just make sure that the larger pattern that you're after, it's a data point that fits. Okay? All right, let's go 30 degrees. What if I divide by cosine of 30 degrees? Let's check this out. 5.77. Maybe I'll call it 5.8. Maybe if you're measuring on a spring scale, you could just call it 6, right? How much precision can you get? So it went up a little bit, not a lot, but a little bit. Interesting. Let's take that angle all the way to 60 degrees. 60 degrees. Wonder what's going to happen. Ooh, 10 exactly, like on the nose, 10.000, like 10 newtons exactly. Huh, you know, that makes me want to pull out some paper. But why would it match the weight? The weight was 10 newtons. Now at a 60-degree angle, we're getting each spring scale is also matching that weight. What's up with that? Okay. So I got, definitely I got 10 newtons pulling down this way, 10 newtons. Okay. And I've got these spring scales at, let's see, 60 degrees from the vertical each. That's like bam, bam. Let's make that a little darker right there. There we go. Right. So that this is 60 degrees right here. Right. Right. And supposedly this should come out to like 10 newtons. And I guess by symmetry, this would be the same idea, right? Right. Right. Huh. Hey guys, what's the total angle between these two spring scales right here? Is that 120 degrees? Oh, because what's this angle right here? 120 and 120. Hey, do you guys see it's like some radial symmetry type, right? Let's change the story on this. Let's make this donkey and the 2 guys pulling the donkey, right? Right? Or maybe it's 3 guys playing the tug of war. You got a 3-way tug of war with ropes. Got three ropes of tug of war. Aerial view. We're up in a helicopter. You guys imagine that? We're looking straight down on a big field. There's 3 guys tug of war, or maybe the donkey if you like the donkey, right? And the fact that there's radial symmetry and they're static, they're not moving. They're they better all be pulling with the same force, right? Okay, so that there's a symmetry perspective on what we got from the trigonometry. It leads to the same outcome. Is it? Right. Let's go one more. Let's just bump this up. 20 more degrees. Okay, I mean it's been bumped up a little bit. I wonder what happens if I put in 80 degrees. What do you guys think is going to happen? Whoa! 29 newtons. What the heck just happened? 29 newtons. Because look, I was bumped up 30 degrees, and then 20. This only went up not even a newton. Oh, okay, a few more newtons. And then it jumped all the way up to 29 newtons. What the heck is going on there? Let's make a graph of this, and then we'll get some kind of insight out of that. So this says the force of each top spring, say in newtons, as a function of that angle from the vertical. Looks like my largest value, let's put that at like 30 newtons. So 0, 10, 20, 30 newtons. 10, 20, 30 newtons. Okay, plot some points here. 0 degrees, each top spring was 5 newtons. 30 degrees, each top spring was almost 6, so it bumped up a little bit, but hardly anything. At 60 degrees, okay, now we're up to 10 newtons, right? And then at 80 degrees, woo, it's starting to like fly off the chart here almost. It's up to 29 newtons. Huh, that is a really weird looking graph. What would happen if you took this angle all the way to 90 degrees, which is another way to say you're going to make a perfect T shape, right? I wonder what the math says there. What is cosine of 90 degrees? 0, right? What happens when you divide by 0? The universe blows up. Look at that. Right. So graphically, that translates into a what? A vertical asymptote. Vertical asymptote. Okay, you guys see this is going to be asymptotic? That's what's going on. Okay, so for the first few degrees, yeah, the force picked up a little bit, but not a whole lot. And then, woo, then it really races. It takes off. Right? And then it heads off towards a vertical asymptote. Is that? Okay. So as this angle from the vertical approaches 90 degrees, what does the force in each top spring approach? Infinity. You guys are thinking infinity, right? Right. Therefore, can you ever make a perfect T-shape? Perfect T-shape? Is it possible? Yeah. Yeah, can't do it. Right? Because here, let's go back to this poster. Right? If you were to make a perfect T-shape, what you would effectively be saying is that these vertical components could no longer exist. And you guys know that can't be true. There better be some vertical components here. In fact, they better specifically be 5 newtons and 5 newtons to balance out a 10 Newton weight, because you have to satisfy this condition, right? So yeah, you can't make a perfect T. Okay. When you walk across the floor is made out of physical materials. Think you're depressing the floor a little bit, tiny bit, right? Floor's responding. Civil engineering. The chain gang. Got scale, weight, scale, weight, scale, weight. I'm gonna just make up some numbers again. 1 kilogram, 1 kilogram, 1 kilogram. You may use different weights, that's fine. Okay. Now for, what does my top scale read? How much total weight is it holding? How about 30 newtons? Has to hold everything beneath it. Okay. What do you think my middle scale is reading? 20 newtons. Ooh. What is my bottom scale reading? Yeah, 10 newtons, because it's only holding the one weight beneath it. Ah, yeah, you guys see that? Huh. Okay. A heavy metal chain suspends a weight. So there's some old chain just hanging in a warehouse, been hanging there since 1940. It's got old, rusty. Some of the links are ready to go. Which link is probably going to break first? One near the top, right? So like that, right? Now there is a variation on this question here, which if you turn this horizontal, let's turn this into a train. Choo choo, choo choo. Guys see the train? If there's a train engine and it's pulling all the cars behind it, ooh, what's the deal with the tension in the links from car to car? Do you think the first link behind the engine has to pull all the cars behind it? So there's going to be a lot of tension. Versus if you get near the back of the train and the last one is just pulling the caboose, do you think it's not nearly as much tension to pull it? Right? If the train's accelerating, that I guess that's part of the condition too. If it's the whole thing's accelerating, yeah, more tension near the front than the back. Right? There's the horizontal version. There's the vertical version. Right? Be ready to field both of those. It can usually ask like one of those questions every exam. So right, be look for that. Right. Ooh, let's slip another friend into the chain gang. Right in the middle there. Oh, this guy, 1 kilogram, 1 kilogram, 1 kilogram. Do you guys think my top scale is still holding up 30 newtons of weight? You guys think my bottom scale is still holding 10 newtons of weight? Okay. Now here's the question though. What about the middle scales? Is it going to go 20 and 20 or 10 and 10? 10 and 10. Yeah. All right. So that's what you guys saw yesterday, right? Okay, so the weight like splits. The 4 splits. Right? You guys got that? All right, let's put some motion here. Ooh, elevator weight. Okay, so you guys have been in elevators, right? Elevator doors closed, and depending on which direction you're headed, up or down, you feel something, right? You feel something, right? Actually, you probably only feel something for like a fraction of a second. And then once that elevator gets going, constant velocity. Can you feel constant velocity? No, it feels like just sitting in this room, doesn't it? Right? So you don't feel velocities. You do feel what? Accelerations. Yeah, so something you feel, there's some kind of acceleration type going on, right? And you guys know those are different concepts, right? Velocity versus acceleration. So when I say accelerate this thing upward, right, that may or may not mean that it's moving upward. Right? It might, but it might not. Right? There's 2 different ways to do this. Right? So accelerate it up. What's the most obvious way to accelerate something up? To pull it up how? Faster. Exactly. Yeah. Right. So if you start from rest and you begin to pull it up, that's accelerating up. Right. Or if you pull it up faster. Okay. However you do that, what's happening to the force reading on that spring scale? Increase. Yeah, exactly. It's gonna increase. Right. If you're staying in an elevator on a bathroom scale, and let's say you're on the ground floor and you want to go, I want to go to the top of the building. Take your time. Right? When that elevator starts to move up and the floor is being pushed into you, you think that scale rating is going to show a larger apparent weight, maybe again for like a fraction of a second, right? And then when the elevator's constant velocity, it's just like sitting in this room, right? Now, there's another way to also accelerate upward that's maybe less obvious. Can this whole system move down and also accelerate up? Guess if it's doing what? if it's slowed down, right? Yeah. So if you lower it to a stop, right? You might be able to see that. If I slowly lower it and then I stop it, you guys see how the force rating jumps up? Right. If you're on the top floor and you get jumped in the elevator and you're going down, and then the elevator slows down to your destination floor, slows down. Then right that moment for a brief second, you'll also feel a little bit heavier, and the scale will reflect that. Okay. There's two ways to accelerate up. Okay. Now let's switch over to accelerate down. What's the most obvious way to accelerate down? Move down faster and faster, right? In fact, an extreme example of that is you could just cut the elevator cable. Then what would you feel like? Weightless. You also could have said terrified, but I'm going for weightless, right? That'll be an extreme example of like a downward acceleration, right? Yeah, so definitely decrease, right? Again, an extreme case like free fall, all the way to zero apparent weight, you feel like an astronaut, right? What's the other way to also accelerate downwards that's less obvious? You could lift it and do what? Slow to a stop. Yeah, when it's lifting and slowing to a stop. Okay? So if you're on the ground floor and you're in an elevator going up to the top floor, as you slow to reach your destination floor going up, okay? Maybe for a fraction of a second, you also lose a little bit of apparent weight. You feel light. Okay, right, guys good? Okay, next one. This one here, tie together a couple spring scales with a string and accelerate the top one right or left. Right. This is actually very similar. These two are pretty similar in concept to each other. Here I just broke it down to 4 scenarios. So let's look one scenario at a time here. When the top scale is moving left and speeding up, moving left, speeding up, you really pull it faster, faster to the left. What do you think is happening to the tension in that string? Increasing or decreasing? Increasing, yeah. So now that's an increased force ratings in the scales and then the tension. Okay. What if you're moving the top scale to the left, right? But it's slowing down? What do you think happens? Is that more tension or is that more slack? In fact, in extreme case, yeah, more slack, right? More slack. There you go. Extreme case might be like, what if you pull it to the left and just like let it go, so that it like very quickly slows down, right? Next one, top spring is moving to the right faster and faster. Right. Is that more tension or more slack in that string? More slack. Actually, these two are like almost identical physically, like if you don't focus on the velocity or the direction of motion. Right? Extreme case could be you start from rest and you just let it go. Right? You just let it go. Yeah, there's a little tension, so it pulls the sky along, but I bet there's a lot less than holding it at rest. Right? And finally, the top spring is moving to the right, but you bring it to a stop. Does that mean that maybe you're applying a huge leftward force to bring it to a stop? Is that going to increase the tension in that string and the force ratings? Yep, we do that right there. Okay. You guys got this? Right. Hopefully you got those, but not then. Hopefully those explanations made sense. Right? Yep. Okay. All right, next one, friction. Right, so this one, we're going to do a more extensive version of sometime in the next couple of weeks. All right, so here's an intro. Lift an object versus drag it. Right, so if I lift this object, maybe it's reading like 5 newtons. Let's try a different scale. There you go, 5 newtons. Versus if I drag this across this paper, now it's reading about 1.5 newtons. Now I'm dragging at constant velocity. That's an important aspect of this. Right here. Right. So right, let's go 200-gram object, 500-gram object, and 1,000 grams the kilogram. Right. The force to lift it would be like 2 newtons, 5 newtons, and 10 newtons. Okay, so we know that from before. Right. What about dragging it though? Right. Now I just did this guy right here, and I was getting about 1.5 newtons. What if, oh, whoops, I forgot that one. Okay. Let's call this 3 newtons. Just make believe. Just want to show you guys ideally. Right. Let's say I drag the 200-gram guy across and it takes, let's say half a newton. Thereabouts. Right, something like that. Okay. Right. Those could be realistic type numbers. You probably got something similar yourselves, maybe something kind of like that. Right. Now, I do want to, here, let's go ahead and answer this. Right. So, in general, what takes more force, to lift it or to drag it? What's generally more force? Lift it. right? Lift it. Okay. Yeah, that's not 100% time necessarily always true. Let me give you guys a counter example. Okay. Now, it's very rare to take more force to drag, but it's possible, right? For example, if you have a car with brand new tires on a brand new paved road and it's dry, so it hasn't been raining for a while, right? It's possible that the conditions between those two materials might be such that it's actually easier to lift the car than it is to like drag the car across the road. I'm not talking about the tires rotating. It's like what the wheels are locked in place. Right? It is possible, right? And speaking of that, materials, and this is related to like a material properties. What I'm trying to get. Like if you take the ratio of these last two columns, 3 over 10, is that 0.3? 1.5 over 5. Ooh, that's the same ratio, isn't it? Right? 0.5 over 2, that's like 0.25. That's kind of close, right? This ratio I'm talking about is something called the coefficient of friction. You may call it about 0.3 for this particular case. That's to say that the drag force is like 30% of the lift force, or something like that. Right? Now, get to talking about materials. These are, this is a material property. You guys see this like black paint versus this paper, right? There's some material property that would allow for that ratio to exist, right? Like this 0.3 ratio, this 30% ratio. Do you guys think if I replace this regular paper with wax paper, where it's real slick, might need a little tiny force to pull it across the constant velocity? What if I replace this with sandpaper? It's like, you guys think that would change things too? Okay. So actually, if you compare these two, it's kind of like apples and oranges because we're talking about black paint versus like bare metal, right? So can't exactly compare this, but maybe get this idea. Okay. All right. Oh, and here, last thing I want to say about that is on this table, you guys got first day of school, mu, coefficient of friction. This is one of the few unitless numbers in this class because it's newtons per newton. So that cancels out and it becomes unitless. Okay? So we're talking about ratio of friction force to what's called the normal force. You guys will see next few days. Okay? There's actually two different kinds of friction. There's static versus kinetic. So if two surfaces are not moving relative to each other, it takes a lot of force to overcome, like initially break that friction, and then not as much force to keep it in motion after that. So that's static versus kinetic. All right, so just plant some ideas there. Gotta say that. All right, buoyancy. All right, this one, I don't know how well this worked with you guys, but I'm just gonna pick one object and run with it. Let's say I got a 1 kilogram object, so the big guy right here. Boom. And I weigh it in the air and I get 2 newtons. Okay, maybe I dunk it in the water and I get something closer to like 9 newtons. Right? You might have noticed a small difference. You might not have noticed any difference at all, you know, just with the precision of the spring scales and stuff, right? But it may have been a small difference. You may have seen that, something like that, right? So let's look at what I'm going to call a free body diagram for these two scenarios, where I'm just labeling the forces on those masses right there. Okay, so when you hang it in the air, this thing weighs 10 newtons. So weight is 10 newtons. And the spring scale force pulling up would also be 10 newtons. Okay, so 10, 10, boom, done. It's in equilibrium. Okay. When you put it in the water, it's a little bit different. Right? We got so the gravity pull is still 10 newtons, right? That didn't change. The Earth's pulling on that. Okay. But the spring scale does look a little bit different. It doesn't look like as much. The force from the spring scale might only be like 9 newtons, because there's also the support force from the surrounding fluid called the buoyant force, which would be about 1 newton or so for that case. Okay? Really, no, it's really subtle for this particular setup because these lab weights are so dense. Right? They don't occupy a whole lot of volume of water. Right? Do you guys know something about like Archimedes principle, possibly? Like it's the buoyant force, right? I might spend like all of a minute next semester telling you guys about it. This isn't going to show up in the AP exam, but I'll show it right here. The buoyant force is mathematically equivalent to the density of the surrounding fluid, in this case the water, times the gravity field of the Earth, 10 meters per second squared, times the displaced volume, say displaced volume, right? Which is also equivalent to the weight of water displaced, which again is pretty small compared to the weight of the object itself in this case. Now, if you had something that was a density that was closer to that of water, this would be a more apparent. It might be like this might be 6 or 7 newtons instead of 9. Okay, you guys kind of get that? Okay. All right, last one here. Last one's more of a thought experiment. I didn't want you to do this because it might be a little bit too dangerous, but what if you will this into like a circular pattern? Now, there's multiple ways you could interpret this. So one interpretation is you could have thought, well, what if I wheel this around like a conical pendulum, make like a cone shape? You guys see like a cone shape that could be, right? It could have been one interpretation. If you did that, here's what the forces would look like on this object. I got its weight pulling down. Okay, so Earth's gravity is always pulling straight down. Okay, and the spring scale is pulling up and to the left in this case. I'll call it F sub S. Okay? I could break that spring scale force into components. Say, well, it's kind of pulling it up. It's kind of pulling it in, right? And do you guys see the vertical component of the spring scale force balances out the weight pulling down? You guys see that? So the sum of the forces in the y direction zeroes out for, if you interpret that as a conical pendulum, which means there actually is a net force. There's a force pulling in. That has something to do with the changing direction. It's called centripetal force. We haven't talked about that in class yet. Save that for a few weeks, but you guys can see how that could kind of go together, right? Right. In that case, if you interpret it like this, guys, what's larger? What's the larger force? The spring scale force or the weight? It has to be the what? Has to be the spring scale force, because this component is equivalent to the weight, and the largest side of a right triangle is the hypotenuse. Yeah, the spring scale force has to be greater than the weight itself, right? You could have interpreted it. What if you did like a vertical circle, right? Now, if you wheel it around real fast, like a centrifuge, I bet the spring scale force definitely would have been larger than the weight. What if you do it kind of slow, like, right? So it like barely gets around the top of a vertical circle, right? Could you imagine the spring scale force might actually get smaller than the weight? Possibly. Could happen, in which case the answer would actually reverse the other way. But if you were a ladybug along for the ride, you might feel a little bit weightless near the top, right? Maybe, right? So different interpretations of that one, different possible answers. All right, you guys get there? And so hang on to this for about 10 minutes. I want to switch over to Newton's laws of motion, and then I'll have you guys just turn that into the gray tray before you leave class today. All right, so let's look at Newton's laws of motion. Oh, I should ask you guys before you guys see this. What is Newton's first law of motion? Newton's first law of motion says an object at rest, say at rest, an object in motion will, yep, just wants to keep doing what it's doing. There you go, right? That's also called law of inertia. If you hear law of inertia, that's synonymous with Newton's first law of motion. Right? So an object at rest will remain at rest. An object that is in motion will maintain its velocity. Now you guys know velocity has two aspects to it, speed, but also direction of motion, right? And that'll continue to be true until an external force acts on that object. Okay. So my classic example is this guy right here. Guys, what is this picture of? Voyager. Oh yeah, Voyager. I've had two students get that right today. All right, nice. Yeah, Voyager. That's the Voyager spacecraft. This was launched way back in the 1970s. Back in the 1970s. Okay, and now it's like at the edge of our solar system and leaving our solar system, and it's just going. It's just coasting. It's been going for decades. Ooh. Any gas stations out there in space? Gas up with Mars? Right? How's it going? What happens when it runs out of fuel? Is it going to break to a stop? No, because for it to break to a stop, relative to something else, it would have to actually change its motion. That would require an external force. It's just going. It's just going because of inertia, right? Well, hang on a minute. Why doesn't that work with your car? If you're driving your car and you want to maintain constant speed, maybe you have to press a little bit on the gas pedal. Why is that?
Ground function again.
There you go. Frictional forces, right? Maybe a little bit of friction from like internal, from the ground, all that air drag, right? Yeah. Okay, so you have to counter that force with applying from the gas pedal, so you can push the tires against the road. Yeah. So the net force would be zero, but you have an input force that resists other force. But yeah, out in deep space, the fundamentals of physics really pop out, including like Voyager spacecraft. Okay, it's just going. There's no reason for it to speed up, slow down, or change direction. Right? It's just going. Okay. What is before I flip the slide here? What does Newton's second law of motion say? Does anybody know? Ooh, that's all right. Yeah. Okay. So okay, I think you guys know this. I think you guys know these, right? So second law of motion. A lot of times it's just written very simply as this equation right here: F equals ma. You guys seen this? F equals ma. Right. Now we say F, we're talking about a force, and we're specifically talking about a net force because there might be multiple forces on an object. Right. M refers to the mass. A is acceleration. I really prefer the fraction form myself. I think this shows cause and effect a little bit better. Right. What causes accelerations? A net force acting on a mass. That's what, right? Why would something ever speed up, slow down, or change direction? Something with an external force. Right? So you guys know what acceleration is. You guys know it's a rate change of velocity. So we know about speeding up or slowing down. A few weeks from now, we'll talk about change of direction, like centripetal. Right? We'll bring that in, right? But so the acceleration of an object is directly proportional to the net force acting on it. So if you triple the net force, it's going to triple the acceleration. Right? This also tells you something about the direction of the force. Like if you have a soccer ball set in the middle of the field, right, and there's like 10 different kids coming kick it at the same time, and they go same time. Okay, well, I'm gonna take those 10 forces, kick forces, I'm gonna break them all into components. It's like how much in the X direction, how much in the Y direction, and figure out, okay, it looks like net force is going this way with some magnitude. So that's gonna be the direction of the acceleration during all those kicks, right? Some kind of net force, right? Net force is as if there's a single force acting on it, right? Right. And also that acceleration is inversely proportional to the mass. Let me show you guys that's true. Little mass, big mass. Okay. What if I put the same force on both those objects? What's gonna happen? Let's test it out. Fly across the room. Barely moves at all. Okay, the larger the mass, the less the acceleration. Right, there's that. Newton's second law of motion, right there. You guys good with Newton's second law of motion? Right. Let me see if you guys really get this. Really get this. Right. So question time. Right. Suppose you have a net force on an object. Maybe it's a car, maybe it's a particle, maybe it's a cannonball. There's a net force. Does that net force result in a constant velocity or a constant acceleration? Which one? Constant acceleration, which means velocity is changing, and velocity can't be constant. If there's a net force, there is an acceleration. If you ever see a constant velocity, that means acceleration is equal to what? 0, which means the net force is equal to what? Also 0, right? There might be individual forces, but the net force would be all zeroed out. Right? Oh, I was gonna ask you guys Newton's third law of motion, but you guys would have said for every action equal opposite reaction. I'll say for every force, there's an equal opposite reactive force, right? So we're considering two objects, like object A, object B, right? They're pushing or pulling on each other somehow. So for every active force on object A by object B, there's a reactive force, equal in magnitude and opposite in direction by B on A, okay? So some version of this, right? Got a couple of classic examples here. Cannon and a cannonball and cannon, okay? And then some kind of blast in there, the cannonball flies out. Now, is there a force on the cannonball? Yeah, for sure. That's what gets it going in motion, flying across the field. Is there also a force back on the cannon? Yeah, maybe it has a little bit of a recoil, right? But which force is bigger? They're the same, right? Same. Really the same force? Really the same force? Right? Here's what's going on from the point of view of the universe. From the point of view of the universe, there's just some explosion that happens inside the barrel. It's just pushing everywhere in all directions, all the same, right? The motions of these two objects is really different, though. The cannonball like flies out really fast. The cannon hardly moves back at all. Why? Because those two objects have different what? Masses. Boom. Okay, that kicks back to Newton's second law of motion. Little tiny cannonball, huge acceleration. Big old cannon, little tiny acceleration. It's got a recoil, but only a little bit. Okay, so you'll see different effects, right? This is difference in like change in motion, different effects, right? But the forces are always the same. Let's do another example. The moon and the earth, right? Is the earth pulling on the moon? Yeah, that's what's keeping the moon in orbit, right? Is the moon pulling on the earth?
Yes.
Yeah, right. That's why we got tides and stuff, right? But which force is bigger? What?
No, they're equal.
Equal, right? It's the same force. Right? Really? How is this the same? Does the earth wobble a little bit? Yeah, there's a little bit of effect. But the moon, a huge change in motion for the moon, right? So like it's a centripetal type force, right? Because the earth has so much more mass, there's a lot less change in its motion. That's what that's about. Okay. Now this is a law that almost everyone can say the words, but to actually like intuitively have this in your gut is that's a step trickier. So I stole this example off a YouTube channel called Veritasium. You guys know that? Right? This is one of his first videos way back in the day. Right? He says, well, imagine it like this. Suppose you got different mass objects and they're gravitationally pulling on each other. Okay? Let's split this into piece by piece. So those two, now if they're equal mass, maybe it's pretty obvious that they do an equal pull on each other. Okay, so equal mass, equal gravitational pull. Right? These two guys, equal gravitational pull. These two guys, equal gravitational pull. Right? Now let's see the cumulative effect. Now do you guys see why even if the two objects are different masses and they're gravitationally attracting, it's still the same force between them? Same force, right? And finally, for the bell rings here, tomorrow we're going to start in earnest on free body diagrams. I got a whole PowerPoint already uploaded to Google Classroom. So all we're looking at for this type free body diagram is I want you to label all the forces acting on an object. In December, we'll talk about moments and torques, but for now, in the next few weeks, I just care about forces. Right? If something's in motion, are you going to label velocity vectors on this type diagram? No, so no velocity vectors. I might indicate velocity for some reasons, but you really care about force vectors. So we're going to take all tomorrow to do a bunch of these type diagrams. Okay? Here's an object in free fall. Here's what you did yesterday with your lab. You guys remember pulling spring? Now, if you pull it across the constant velocity, that means zero net force. That means these two are canceling and these two are canceling. So some version of that. All right, bell's about to ring, so go ahead and pop your lab in the gray tray, and that's going to be our pause point today.